Hello students, welcome back to the next lecture, which is the lecture number 23, and quickly we can move on to the place where we have left out in the last class. Now the meaning should be clear that they are representing the distance of separation, and clearly this is also a scalar value. Okay, that point is also clear, and therefore let us express them in a proper notation saying that it is three-dimensional system. Now, the representation for the three-dimensional system will be becoming clear when you write down first in Cartesian system, and therefore we can always write like this. So once the clarity is there about the way in which you are going to write, and if this is comfortable to you, then this Lagrangian can now be converted to the three-dimensional spherical polar coordinate system. The Lagrangian is actually a function of r comma. So there is an r here. Then you have a theta dot and phi dot. It's time to search whether any of the coordinates are missing in the equation. Okay, so it's very clear that by comparing the original expression here and then the list of variables written down here, what is missing is very clear that this quantity, namely the phi, is missing in the Lagrangian. And the moment this is missing, you know what to do now. Okay, the meaning of the missing quantity is giving an indication that there is a symmetry present in the system. That is the meaning. The quantity which is absent there, it has that symmetry. Since now angle phi is absent, it has a spherical symmetry in the phi direction. So our conclusion therefore is that since this phi is missing, we can quickly calculate the dou Lagrangian divided by dou phi, which is certainly going to be 0 because it is missing. But however, we can now write down the corresponding. This is clear because of the missing, and not only that, our Euler-Lagrange equation tells that d divided by dt of dou L by dou phi dot. This is the standard Euler-Lagrange equation. This should be equal to this fellow, namely dou Lagrangian divided by dou phi. So which means that you can clearly see that this right hand side is 0 here, and therefore d by dt of what is dou L by dou phi dot? Let us evaluate dou L by dou phi dot from this expression. I will be having half. Let us evaluate the differentiation, half m into with respect to phi dot I am going to evaluate, therefore I will get r square sine square theta. All that will be equal to 0 on the right hand side. So constant, no need to worry. So you can remove them. And what is left out is therefore. So this is the important conclusion that we are going to write down, but mathematically this is fine. Okay, mathematically you are writing some equation and saying that is a constant. But however, you'll have to realize what is the meaning of this equation. So this is the place where you have to think carefully. Okay, so you know what is this one, because phi is absent in the Lagrangian. We ultimately have some quantity to be constant. Now you'll have to realize what is this quantity, and then we can make some conclusion. The point to be noted is that whenever a particular coordinate is missing, this is a coordinate, phi is a coordinate. When a coordinate is missing, then the corresponding means conjugate. We say that conjugate variable. So the corresponding conjugate variable happens to be momentum, because coordinate means next one is momentum only, because this kind of pair is only there in the mechanics, and therefore automatically we say that the corresponding momentum will be written down by the symbol p. P is the standard symbol, and since phi is the quantity that is appearing here, you'll have to put that phi in the suffix. So this is known as the conjugate to the phi. If you are going to have the radial direction, then corresponding quantity will be written down as the momentum and then put the suffix. If you are going to have the standard XYZ directions, then it is easy to understand that we will be writing px. So now the symbols are clear, right? If x is missing in the equation, then the corresponding momentum will be denoted by the symbol px. If r is missing, then we will be writing pr. If phi is missing the corresponding quantity, we will be giving the symbol p phi. So symbol is fine. Okay, then what is the meaning? If you are coming here, the meaning is quite clear. It represents the momentum in the x direction. Okay, whether it is linear or angular, that terminology will not come. That terminology you will have to understand after this statement. So the statement is x component of the momentum is conserved. That is the meaning of this. When x is missing, If x is missing, then how do you read? We read like this. Then x component of the momentum is conserved. Now the question is x component of linear momentum or x component of angular momentum. That kind of doubt will come. Now what I am trying to say is, now there is no more doubt. Why there is no more doubt is, x component means you are talking about x-axis. X-axis is straight or it is curved. That's what you have to see. X-axis is straight, right? X-axis won't have a curvature. Now since x-axis is a straight line, the momentum should be linear momentum. So therefore, that clarity, when it is coming, you will never get a doubt which is angular momentum and which is linear momentum. Now come here. In the case of the spherical polar coordinate system, when r represents the radial distance, then in case if the r is missing in the equation, then we say that the corresponding momentum will be conserved. What kind of momentum it is? It is the momentum in the radial direction. What is radial direction? It is the direction along the radius, and the radius is a straight line, and therefore the momentum is a linear momentum. Okay, come here. Now the phi is missing. When the phi is missing, then the corresponding momentum will be given the symbol p phi. Okay, now what is the phi direction? Phi direction means, that's what I told you, that the phi direction is the one corresponding to the horizontal circle. So if something is rotating like this, for instance, so you can now understand what is this. And if some certain thing can rotate, isn't it? Certain thing means what? The earth can rotate like that in the phi direction. So now we can measure the phi. This is the initial position, that is the final position. I can now measure the phi in the horizontal plane. Okay, so now you understand what is phi direction. This is the phi direction. This direction that you are going to travel is known as the phi direction. Phi direction. DIREC. So now you tell whether the phi direction is a straight line like x-axis or it has a curvature. Okay, it has a curvature, right? It is in the case of the spherical polar coordinate system, the phi direction is along the circular path, and therefore phi direction has a curvature, and therefore the momentum should be an angular momentum. Phi is angle. Phi is angle means momentum should be angular momentum. So our conclusion or our understanding is that phi is representing the angular momentum. So our conclusion is that whatever that you obtained now, which is mr square into sine square theta and phi dot is constant, that's okay. But what is this quantity? So that is what we are interested in. What is this quantity is, since phi was missing in our equation, this quantity should be equal to p phi. That is exactly what I am trying to explain. Which means that the angular momentum due to the motion of the planet in the phi direction is a constant of the motion. And remember that constant means constant of the motion. Now we have discovered one constant of the motion in our system. But there is much more to understand clearly. Let me explain further now. Is this correct? That is what I am trying to say. So this terminology is not the same here. So, okay. So this terminology we will not use. We will not say that angular momentum in the phi direction, but rather we will say that angular momentum due to rotation in the phi direction. So the English is now different. You please see the difference. Angular momentum in the z direction is there. Here it is not in the. It is due to the rotation in phi direction, and therefore, so you have to think a little bit and understanding what is that we are trying to say. Okay, so let me write down an arrow like this. You take a cricket ball and then you spin in the horizontal direction like this. If a cricket ball is spinning in the horizontal direction like this, what is the direction of angular momentum? So that is what you will have to think. It is there all the time from your school level physics. So you have to refresh your memory. And if you refresh your memory, we say that the angular momentum is this vector. I mean, it is vertically up, and we say that it is a z direction. So now you see how the things are connected. When a particular object is rotating in the phi direction means horizontal rotation in the horizontal plane. When it rotates like that, angular momentum is in the z direction. Okay, I am giving the importance to the word in the. Okay, please see this. So angular momentum will be in the z direction. Okay, that will be written as Lz vector, because it is an angular momentum in the z direction. The meaning of the p phi is that we are talking about Lz. The meaning of this arrow is that there is an associated vector quantity here, but otherwise the component itself is a scalar, you know that. Okay, p phi is a scalar, component is scalar in that direction. So similarly Lz is a scalar, then it is acting in the z direction. So that is why that is the meaning I am trying to explain. So this vector I am putting. So now the conclusion is that usage of the symbol p phi actually means that it is the angular momentum in the z direction if you are considering a corresponding Cartesian system. So you should also have a Cartesian system on top of the spherical polar coordinate system in order to map the r, theta, phi to the x, y, z variables. So either you say that p phi is a constant of the motion, or you say that Lz is a constant of the motion. Both are equivalently the same thing for the same physical dynamics. Once you have the Hamiltonian for a given problem, you can tell that the Hamiltonian itself is a constant of the motion. Okay, so that is why it is called the first constant of the motion. Now what all you have discovered is the second constant of the motion. Because of this there is a consequence, and this consequence is also not easy to realize unless you think carefully. So that is what we are going to do now. Let us think now. Okay, c is a constant, it could be any number. Okay, by the term constant, remember it could be any number including 0. The only thing is that infinity is not allowed. You can't have infinity there and say that that is a constant, because infinity itself is not a number, and therefore we can't accept that infinity is a constant. So other than infinity, you can have any large number, that is fine, it's acceptable. 0 is also acceptable. So this is the scenario. Okay, now let us see what to do or how to understand the situation. This being the mass of the planet, we are talking about the mass of the planet, and therefore this is a constant. So we don't believe that the mass of the planet will change as it moves. So to that extent m is going to be a constant, which means that the presence of the m doesn't affect the originality, doesn't affect the satisfying of this particular relation. So whether you are writing m or whether you don't write m, it doesn't matter, which means that I can write down r square into sine square theta into, and this quantity, if you want explicitly, I'll write down d phi by dt is a constant. So for the constant, I'll once again write only c. Okay, you should not think that no, this m is missing, therefore you should write c by m. So let me write down here. Okay, so when this particular please see this, when the mass is now removed here, it apparently means that this m has gone to the right hand side, and therefore you should get a c by m. C by m is fine, but c by m is another constant d. Okay, so why do you want another constant? I will maintain the same symbol c. Okay, so it's all maintaining the symbol for that, not the exact identical numerical value. So the point is now therefore clear. So we will maintain the c as the symbol. Okay, its numerical value will be changing if you divide by the mass. That's fine, but ultimately this remains as a constant. Now comes the important point. Now whether the radius is going to be constant, that is you are typically asking, and right now we cannot make such conclusion because there is no evidence that the planet is going to move along a fixed circle of radius r. Okay, only then we say r is a constant. So we don't believe that, and that is first thing. Second thing is an experimental evidence of the Kepler's laws are basically experimental evidences. Kepler has not done all this kind of calculations, right? So that is clear to you. All the Kepler's work, namely the first law, second law, and third law, they are all based on observational astronomy. Okay, there is no calculations, nothing to do with dynamics, etc. It's all based on the data that is collected by looking at the sky. So therefore, experimental evidence already we know that from the Kepler's law it's moving in an elliptical orbit, and therefore there is no point in making r is a constant. Okay, for an ellipse you don't have a constant radius, so that is rejected. So r is going to be a variable. At least you note down that. Let me write down that this is going to be a variable as a function of time. By variable, what I mean to say is that it is a variable when time changes. This is the first point. And what about the theta? Theta is the movement of the planet, and since the planet doesn't move in straight line, rather than saying movement, we will say rotation. So it is going to make some kind of an orbit. You already know that it is making some kind of a closed orbit like elliptical orbit, and therefore theta has to change. That is the meaning of that. If theta is not changing, then the planet has to stay in one place. Okay, so that is also not true from an experimental evidence, and therefore we will make a conclusion that this is also a variable. So there are two numbers or variables are there, but on the right hand side you have a constant. Okay, so I have a x is one variable and then y is a variable, and there is something is there here, and this product, there are three numbers are there, and this must be a constant. Now we are asking the question how it can be a constant. That is what is the question. X is a variable, y is variable. So two things are variable, and we don't know what is this because d phi by dt is there. We do not know what kind of thing can be. Now how the primary question that we ask is how this right hand side can be a constant if the so many things are varying on the left hand side. If the three of them are variable, if this is also variable, let me say that this is also variable, three variables will take its own three values, how the product can be a constant. So the conclusion that we would like to say is that this is not an easy thing. Okay, constant cannot happen if three numbers are varying when the dynamics is taking place. So certainly there are two options are there. Certainly the right hand side cannot be a constant. If three of them are varying, what is the right hand side? Right hand side should be a variable. You can't write that. But however, you can't do that kind of a situation because Lagrangian clearly tells that phi was absent, and because of that reason only, from the Lagrangian equation of motion only, we have written that. So if you say that the right hand side is not a constant, then you are going to throw the blame on the Lagrange equation of motion itself. No, which means that is not correct. So you can't agree that the right hand side cannot be a constant. So ultimately what happens is this has to be a constant. There is no option for you. You don't have a freedom to put the blame on the right hand side because it all come from the Euler-Lagrange equation, and we know that it is proved well and it works nice. So the right hand side C has to be a constant. There is no option for that because we already got right now. In addition to that, there is no doubt about the r and the theta. Both of them are variable. So two things are varying for sure, no doubt about that. The right hand side is also a constant, no doubt about that. If it is the case, you ask the question, what is this? The answer is, you can have two possible answers. One is that this can be a constant, or the second option is this can be variable. You can't accept it because if all the three of them are variable, right hand side cannot be a constant, and therefore we make a conclusion that d phi by dt cannot be a variable. You put a question mark. Okay, this is looks like a good option. Can we agree that d phi by dt is a constant? Because if d phi by dt is 10, for example, then you get a c by 10. C by 10 is a constant, so that is what I am writing c here. Okay, we'll keep the c for the whatever be the constant. So r square is a variable and sine square theta is a variable, and still you have the right hand side constant, and this is not possible. And therefore what happens is this option is also rejected. You are compelled to reject. The third option is that d phi by dt has to be 0. Okay, just think about what will happen if d phi by dt is 0. You substitute 0 here, then 0 into a variable into variable. Ultimately it is 0, and the right hand side is a constant. Okay, constant 0 is acceptable. So which means that at all instant of the time, whether it is minutes, hours, seconds, or 1 million year, it doesn't matter. For whatever time it is, the right hand side is going to be 0 if d phi by dt is 0. Then therefore it is the only situation where I am able to satisfy this condition, and therefore this is the only condition appears to be valid condition satisfying the constant of the motion. Okay, the right hand side C means right hand side is a constant of the motion. So our conclusion therefore is, after making this discussion, we make a conclusion that p phi, because all these equations are p phi, right? We have just come down in the board. You just go back here. So what is this expression? Mr square into sine square theta into phi dot is a constant. What is this entire expression? The entire expression is p phi. P phi is a constant of the motion. That constant of the motion is what is this c. So therefore, what is there on the left hand side is actually p phi. P phi means either you say p phi or you say Lz. Both are same. We say that the z component of the angular momentum. Okay. So that is going to be 0. So our conclusion is that p phi has to be 0, or whether it in an equivalent language you can say that the z component of the angular momentum has to be 0. So it is what you call the specialization of the conclusion. The conclusion is this: L is a constant of the motion. Constant of the motion means it is constant. That is good. In addition to that, you have now fixed this constant to be 0. Is it clear? Constant of the motion means it can have any number like 25, 35, etc. Now, it is not only a constant of the motion, that constant is equal to 0. So, that is the conclusion now. So, therefore, this is what we mean to say that our conclusion is that this particular quantity is not only that it is a constant of the motion, the value taken by its the z component of angular momentum is identically 0. So this is the thing, but then all these things happened because of the d phi by dt equal to 0. You are going to demand that, okay? So that is the very important conclusion, and now therefore we will write down that. So that we made our conclusion is, what is the meaning of that? Phi doesn't change as the time changes, means the planet is not going to move in the phi direction. So planar motion means the motion that is restricted to in a particular plane. Particular plane is very important, whether it is horizontal or vertical, that is secondary. So our conclusion is that the particle or the mass or the planet, whatever it is allowed to move only in the vertical plane. And since we are going to use the word plane, it is naturally two-dimensional. So therefore, our conclusion is that this is a two-dimensional motion. Okay, and therefore the dynamics is two-dimensional dynamics. So therefore, what happens is now, because of this reason, we make a big conclusion that the number of degrees of freedom is now 2. So 3 has come down to 2 now, interestingly. So if you ask the question why it is happening, on what basis? Okay, on what basis one degree of freedom has come down? Is the reason is it is because of the spherical symmetry present in the potential. So the answer is that this reduction in the degrees of freedom is due to what reason it has come down is due to. Okay, if I write something like this, you can understand G into M1 M2 divided by R. We are talking about this kind of potential. Okay, in this kind of potential, as you see, only the scalar R is present. It doesn't have the angular dependence. So the moment the theta and phi's are missing in the potential, we say that there is a symmetry present. What kind of symmetry is present means the symmetry can be due to theta or the symmetry can be due to phi. And from the Lagrangian, we discovered that the symmetry present was phi, because theta is anyway present. R square sine square theta was there, so only phi was missing in the expression. So this is a very big conclusion, because now the mathematics is going to come down drastically. Working with the three-dimensional algebra, you know that what you call three-dimensional analytical geometry or solid geometry. So doing mathematics with solid geometry is a little difficult when compared to doing problems in two-dimensional analytical geometry. So is that point clear? Now Kepler's experimental observation says that the planets are going to move in ellipse. And you see, ellipse is two-dimensional, it's not three-dimensional geometry. So which means that what is observed in nature through experimental astronomy, okay, or observational astronomy, experimentally determined, is now verified using the Hamiltonian mechanics. So this is a very major conclusion that what is the major conclusion is that the planetary motion, or the so-called Kepler's problem, is a two-dimensional problem, even though it is moving in free space. So this is something you have to surprise. Why I am explaining so much is that there is some surprises there. See, nature is giving lot of space, three-dimensional space. So for earth and the sun to occupy. So where is the sun and the earth means it is occupying the three-dimensional space, and nobody is restricting. Okay, so now the earth and the sun can move as it feels. Okay, nobody is going to stop it. So when such a scenario is there, the sun and the earth can actually move in some orbit or some kind of a path which is completely three-dimensional in nature. It can move like. But however, it is not moving. That is a conclusion. Even though we have given a lot of freedom in the three-dimensional space, okay, you freely move in three dimension, even then, it is moving in only two dimension. And And the interesting point why this all happens is because of the spherical symmetry of the central potential. And therefore, okay, now you understand, no? And therefore means it is because of the reasons that I have explained. Ultimately what happens is central force problem is something special, because it is naturally restriction. Even though we are not imposing some kind of a constraint in the system, the potential symmetry itself brings the complexity of the problem down. Okay, a complicated problem has become somewhat better problem, easy to handle. So, and because of this reason, the the central force problem is very important topic. And of course, we will discuss. We can discuss more about this. But rest of the thing, once this is clear, the rest of the thing is fairly simple. So what is the rest of the thing is, convert the Lagrange into the Hamiltonian. That's what you have to do. It's quite easy. And once you get the Hamiltonian, you can write down the Hamilton's equation of motion. How many equations of motion you will have to write? Since 2 degrees of freedoms are there, I will have to write down 4 number of Hamilton's equation. And once you write down the 4 equations, they are all first order differential equations. And then they are solvable. Okay, so it's not difficult to solve because already constant of the motions are there. That is the reason. And once you solve this, we will be getting the equation of the orbit. And from the mathematical calculation, we make a conclusion, or from the appearance of the final equation of orbit, we can say that this equation belongs to the equation of circle and that equation belongs to the equation of ellipse. So this is how mathematically, that means based on the Hamiltonian mechanics, we can say, or we can ultimately conclude that the orbits of the central force problem, in particular those of the Kepler's problem, will correspond to either of the circular path or of the elliptical path. Of course, there are the other options are there, namely parabolic path and hyperbolic path. In general, it will happen for the positive value of the Hamiltonian. For the negative values of the total energy, you don't get unbounded orbits. Okay, what is unbounded orbit? A parabola, for example, is unbounded orbit. Hyperbola is unbounded. Circle and elliptical, they are known as the bound orbits. Okay, bound orbit means whatever time that you give, the planet will be confined to some region. It will not run away to infinity. That's the meaning. So bounded means it will be bounded between a certain finite value. Unbounded means the mass will simply fly to infinity. Okay, that's the meaning. So you, from the structure of the parabola and hyperbola, you can imagine that if you are going to travel along the hyperbolic path, okay, something like this. Parabola means this is the parabola, right? If you walk along this parabola, where will you reach means, if I give you infinite time to you, you also will reach infinity. So that is the meaning of the parabolic. If you are going to give a circular path and I will give you infinite time to you, means for all the infinite times you will be rotating or revolving within the circle. So you are bounded. Bounded means you are bounded within these two limits. You will never escape out of this region, right? That is why we say it's bounded orbit and unbounded orbit. So those things are quite simple to evaluate. It is only fairly simple equations to solve, by the way. So, but the main physical concepts I have tried to illustrate, and then finally brought you to the situation where the two-body problem is essentially reduced to the one-body problem, and ultimately the dynamics is going to take place in a plane only. That's a very crucially important point, and we have already discovered two constants of the motion. One is the Hamiltonian, and the second thing is the z component of the angular momentum. And what is more interesting, if you are going to work out further solution, what is more interesting is the another component of the angular momentum, namely the theta component, is also going to be a constant of the motion. So this is very important, and that means that we are now discovering three constants of the motion. So for a two-body problem, okay, I mean to say that 2 degrees of freedom problem, you can at most discover 2n minus 1 of them. This point I already told you, right? In some time back in the discussion of the super-integrable dynamical system, I told you that 2n minus 1 constant of the motion can be discovered. So since n is equal to 2 in our problem, so this means 2 into 2 and then minus 1. So what is that? That becomes 3. So you are supposed to discover 3 constant of the motion, in which case, if you are successful, then the system is super-integrable. So now you tell me whether three constants of the motions are discovered or not. Yeah, it is discovered. The first one is the Hamiltonian, the second one is the the second one is the z component, and then the third one could be represented by the y component of the angular momentum. Okay, so or in terms of if you want in different notation, you can say p phi and this is p theta. So since p theta and p phi, if you are comfortable, okay, use this, because we are in the what you call the spherical coordinate system. So how many constant of the motion you already discovered means Hamiltonian itself is one of them, and the p phi just now you discovered. And if you continue this calculation, you will also discover that p theta is constant of the motion. And now since all the three are discovered, the maximum number of thing is discovered, and therefore the Kepler problem is known as maximally super-integrable system or Hamiltonian system. So because of this kind of a speciality of the system, we say that the Kepler problem is very interesting and therefore very important, and studying more and more about this is very useful even for practical applications, because when you are sending the for example satellites, you'll have to determine the equation of the orbit of the satellite. Only if you know something about the whether it is stable orbit or unstable orbit, only when you know something, then you can think about sending some satellite. So in terms of practical applications also, this is very useful, and therefore learning the two-body problem, especially under the influence of gravitational potential, takes the very, very important position in the study of classical mechanics. So this is the conclusion that I would like to make. Further calculations are fairly simple, so you can see how to solve the first order differential equation, because ultimately they are first order differential equation, and you are going to have four of them. Okay, out of four of them, interestingly, three of them are constants. Three constants of the motion means what? All the three are constant. Okay, so you have four equations and three constants, so the solution is fairly simple. So let us make a conclusion with this, and then probably in the next class I will try to address something on how to understand a tensor quantity, because the topic is now required in order to understand moment of inertia tensor. So for that purpose, okay, to that level, at least we will understand what do you mean by a tensor quantity, and then we will see how moment of inertia can become a tensor quantity for a solid body, okay, rigid body. Whenever rigid body is there, only we talk about the moment of inertia. For a particle, we don't talk about the moment of inertia. So essentially we are going to move to the rigid body dynamics and then learn how the moment of inertia can become a tensor quantity. That we will do in the next class.